Okay, so I know you can't see this, but this says stable. Stable. Okay, so now we want to talk about stability and balance. All right, so here's a car, and outside tire to outside tire. This is called the base of support. Okay, base of support. And here's the weight, right? This is at the center of gravity of the car, right? We're going to worry about that now. All right, now, you know, if you're crazy and you're tipping your car because you're not driving properly, here's the point. The torque, okay, so now, you know, there's rotation, right? So the torque due to gravity will rotate the car back down if the center of gravity is over the base of support. So you can see here, again, this is the base of support. This is the center of gravity is still over this base of support. So everything will be fine, all right? Everything will be fine. Now, if you're really crazy and you're really tipping, now what do you see? So now the center of gravity is not over the base of support, so now you're in big trouble, right? The gravitational torque will cause the car to tip over if the center of gravity is outside the base of support. Okay, great. Now, if you're a gambler, if you have the center of gravity directly over the base of support, I mean, you know, over the pivot, I mean, sorry. So now if the center of the gravity is directly over the pivot, you're balanced. But what happens if somebody just pushes it a little bit? Then you're in big trouble, right? Okay. So basically, whether or not an object is stable or unstable or balanced depends on how far the object is tilted, right? That sort of makes sense. Now, this angle here, this angle is called the critical angle. Yeah, okay? So now the center of gravity is over the pivot. And this is just this goes parallel to the sides of the car. So this is called the critical angle. And of course, if you exceed that critical angle, goodbye. You know? All right? So, okay. Now, the book has one way of calculating the critical angle, which I find a little strange, sorry to say, but I do. And so I think this is the easiest way to calculate the critical angle. So here's the car on the ground, everything's happy. Here's the center of gravity, here's the pivot. So you just draw this triangle, and this is the critical angle. I mean, I think that's the easiest way to do it. But, you know, there's a formula in the book, and you know, you should look at it. Ah, this is horrible. Oh, man. All right, anyway, I'll help you. Okay. Which vehicle has the largest critical angle, the sedan or the SUV? They have the same width, okay? So this width is the same as this width, okay? So which one has the largest critical angle, the sedan, the SUV, or do they have the same critical angle? So pause your video and figure it out, please. Okay, so it's sort of obvious, I hope, right? I mean, this is really, really low to the ground where the SUV's center of gravity is high, you know. So this angle here is larger than this angle here. So the sedan, all right, so the sedan. Okay, so the sedan has the largest critical angle, so the sedan is safer. It's less likely to tip than the SUV. That kind of makes sense, right? If something's really, really high, it's easier to tip than something that's really, really low. And when I say high and low, I mean the center of gravity. Okay, there you go. Let's talk about something called the restoring force. That's actually important for bones, believe it or not. So we're going to talk about restoring force and then something called Hooke's law. All right, so here's the equation for a restoring force. So think of a spring. Think of a spring that's attached to the wall. All right, so if I pull on the spring, what is the spring doing to me? It's pulling back. On the other hand, if I compress the spring, what's it doing to me? Pushing back. So that's what we mean by restoring force. Think of it like this. The spring doesn't want to get bothered. So if you're pulling on it, it says, buzz off. Just leave me alone. I want to go back to how I was. So it's going to pull back on you. If you're compressing it, the spring is saying, buzz off. I want to be left alone. I want to be left how I was before. So it's pushing back on you. So that's why there's a minus sign. So the force equals minus, I'll talk about K in a minute, delta X. Now what's the thing about delta X? Well, come on. If you have a spring attached to the wall and you just pull it a little bit, well then the force that the spring exerts on you is not going to be so much, right? But if you pull it a lot, then the spring is going to pull with a lot of force. Same thing with the compression. Okay? So here's the F, here's the delta X. K is always positive, so because of that minus sign, it's going to have a negative slope. That's all there is to it. Okay, now hold it. Now the K is called the spring constant, and it just has to do with how stiff the spring is. So, you look it up, or somebody tells you, or when you buy a spring, you say, I want a spring with, K equals blah, 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 or something like that. So it's always a positive number. Okay, so this is the whole idea of a restoring force. And again, the minus sign is because how I just explained it. If you pull here, then the spring is pulling back on you. If you compress, the spring is pushing this way on you. So that's called the restoring force, right? It wants to be just left alone. Okay, now, for whatever reason, Randy Knight in the book, he likes to talk about the magnitude of the restoring force, which drives me crazy, but that's okay. So the magnitude of the restoring force, he wipes out the minus sign. So whatever. So here's the force that the spring exerts on you, and here's the delta X. And now it has a positive slope, just magnitude. So the magnitude of the restoring force is proportional to the displacement of the spring from equilibrium. Okay, whatever, all right? Magnitude of the restoring force. All right, here's a question for you. So when using Hooke's law, F equals minus K delta X, what is important? The length of the spring, the displacement of the spring, or what? So pause your video and vote, please. Okay, I hope you agree. Who cares how long the spring is? What's important is how long, how much you stretch it or compress it. That's what the delta X means. Okay, so it's the displacement. Okay, we just got to make sure we understand the signs and everything like this. So here's a spring. It's attached to the wall, so it's really firmly attached to the wall. This is unstretched, right? So it's just, happy, right? Yeah, okay, and we're using the regular coordinate system. To the right is positive, to the left is negative. Okay, so this is called the equilibrium length, right? X equals X equilibrium. So if it's not being stretched or compressed, if it's unstretched, what's delta X? Well, it's 0, right? Okay, that kind of makes sense. If it's being stretched, so here's the equilibrium length, but we pull it this far, what's the sign of delta X with this coordinate system? Well, it's positive. That's what we mean. Okay, and so forth. All right, and again, if we compressed it, delta X would be negative. And yeah, so here it again, like the K just has to do with the stiffness of the spring. All right, here's a problem for you. A 20 centimeter long spring is attached to the wall. When pulled horizontally with a force of 100 newtons, the spring stretches to a length of 22 centimeters. Figure out K. So you need to do this. So pause your video and figure it out. All right, I'm assuming you did it. So magnitude, F equals K delta X. Therefore, K equals F over delta X. Okay, the force is 100 newtons. Now, what's delta X? 2 centimeters, right? 2 centimeters. So 0.02 meters. and that's 5,000 newtons per meter. There you go. All right, number 5, the same spring is now used in a tug of war. 2 people pull out the ends, each with a force 100 newtons. How long is the spring while it's being pulled? So pause your video and figure it out, please. Okay, we're back. This is the same problem as number 4. I mean, basically, here, you know, we had a spring attached to a wall, and somebody pulled on it. Well, here we have 2 people pulling on it, same thing. So in other words, the other person acts like the wall. So it's exactly the same problem, exactly the same answer, right? Same, okay? So, well, it's not the same answer. How long is the spring while it's being pulled? So delta x, right? It's the same spring, so the K is 5,000 newtons per meter. 100 newtons is the force, so delta x is going to be 2 centimeters. So therefore, the spring is going to be 22 centimeters long. Okay? So that's not a big deal. Okay, this one. The same spring is now suspended vertically from a hook attached to a ceiling, and a 10.2 kilogram block is attached to the bottom end. How long is a stretched spring? So before you do it, let me just give you a hint. Well, yeah, I'm not going to give it. So multiply 10.2 kilograms times 9.8 meters per second squared. You should get 100 newtons. Okay? So basically we have 100 newtons in questions 4, 5, and 6. So guess what? So pause your video and figure it out. Okay, this is exactly the same as the other one. All right, it's exactly the same as the other one. So the delta x is also going to be 2 centimeters again. So the spring is going to be the 20 originally plus the stretch 2, so it's going to be 22 centimeters. Okay, let's talk about elasticity. Yeah, this bones. All right, bones. Now, why do we care about restoring force? I mean, you know, we're talking about springs. I mean, who cares about springs, right? Well, you'll see we do. Springs are a really good model for solids, like bones and things like that. Okay, that's why we do it. And this whole idea of restoring force. So here's a metal rod, and it's somehow attached to the wall. And what are we going to do? We're going to pull on it. Okay, we're going to pull on it. Now, I mean, come on, it's steel. You know, we got to really pull on it with a lot of force, right? But and you know, let's say that we use a machine, right? So we use a machine, and we actually pull on it, so it lengthens by delta L. Well, what is the steel doing to the machine? It's pulling back. Agree? Just like a spring, you know? So that's why we, you know, use this. That's why we talk about springs and restoring force. It works pretty well for like metal rods. Okay? So here we go. So this is the cross-sectional area of the rod. We somehow were able to stretch it delta L, which is not going to be very much, right, for steel, you know? This is us, and this is us pulling on the rod. This is the rod pulling on us, you know? So once again, we get F equals K delta X, which is the magnitude of the restoring force. All right, great. Now, you got to be sort of careful here. This is called elastic deformation. Because, why elastic? Because as soon as you you pull, or the machine pulls, and it stretches delta L. As soon as you let go, this thing is going to go back to its original length. So that's called elastic. Okay, elastic. So basically what we're going to do, we're going to model this as a super stiff spring. And we get really, really good results when we do that. Okay, now we kind of have to think, oh, not yet, not yet. Okay, oh, sorry. Now we want to think of this K, okay? We want to think of the K, the spring constant, or the stiffness of the spring. What do you think it's going to depend on? All right, what is K going to depend on? Well, you know, probably the length, right? I mean, agree? It's a whole lot easier to pull something that's really, really long than something that's really, really short, you know? So it's probably going to depend on the length. How about the cross-sectional area? It's probably going to depend on that somehow. So it's going to so K, so So this is K. K depends on L, A, and you have to admit it's going to depend on the material, right? I mean, it's pretty simple to pull, you know, like rubber or something like that, but it's really hard to pull metal, you know? So it's going to depend on the type of material. Okay, now there's something called the Young's modulus, which is Y for young. Isn't that nice? There's something called the Young's modulus, which gives us an idea about the strength of the material. Okay, so here we go. Here we go. So the restoring force is this. So F equals K delta X, all right? And then we're going to say that K equals YA over L. YA over L. Okay, now instead of saying delta X, I'm going to say delta L. That should be okay, right? Delta L. All right, same thing. Okay, so in other words, okay, all right? Okay. Now, this is true, but it's not so useful. So what's better, what we really want to do is we want to divide by the A. So just give me a minute. So I'm going to get rid of this and put a force here. Okay, so that's the equation. Now we want to divide by the A. So divide this by A, divide that by A. All right, now, why do we do that? Okay, and let me write this different. So this is Y delta L over L. Just let me write it a little bit differently. It's nice to write it like this, you know, because then we don't have to worry about units. If they have the same units, we don't have to convert to meters. It's just nice. Now, why do we want to do that? Well, here's why we want to do that. This is called stress. This is called strain. All right, so the stress is the force over the area. The strain is the delta L over L. Remember, this is just a constant, right? This is something you look up in a book somewhere or determine experimentally, the Young's modulus. So this is a constant. So if you have something equals constant times something, it means that this stress is proportional to the strain, which kind of makes sense, right? I mean, if you're going to pull this a lot, so the delta L is kind of big, you're going to have some gigantic force, right? On the other hand, if this is really small, it's not so much force. So that's the big deal. Stress is proportional to strain. Awesome. Okay, now, oh, horrible. Oh, man. That's nothing I can do about it. Okay, so sorry. So this is the force that we're exerting on the steel or the bone or something like that. And this is the delta L. Okay? And you can see here that the force here is this is a line, right? This is a straight line. Agree? From here to here is a straight line. So that means that the force is proportional to delta L. Well, okay. All right, that's cool. All right, that makes sense. So what does that mean? Well, that's a restoring force, right? That's nothing new. So that's cool. Now, after you pull it to a certain point, then it's no longer linear. See how it doesn't become a line anymore? I'm going to say it's not a line anymore. But still, okay, so this is called the linear region. The linear region. And this picture's in the book, so don't worry about it. Okay, so this is the linear region. And then this here is the elastic region. What does that mean? It means when you let go, it will go back to its original length. That's all, right? So you remove the force on the rod or whatever, the bone, and it goes back to its original length. So it's called the elastic limit. All right, so what if you pull it even more? Okay, oh golly. So if you pull it, so now, again, this is delta L. So if you pull it, if you just keep pulling on that bone or something like that, past the elastic limit, it's not going to go back to its original length. It's going to be permanently deformed. And then, if you keep it up, it's going to break. Okay? So that's the breaking point. All right. Now, what you want to know is the breaking point, right? You don't want to break things. You know, like if you're a doctor and you're setting somebody's leg for a broken bone and you don't want to put too much weight on it or too much tension on it so it breaks. Okay, so let's talk about the breaking point. Okay, breaking point. Okay, so remember, we had stress is proportional to strain. So the maximum stress right before it breaks, okay, the maximum stress before it breaks, that's called the tensile strength. So you can look this up in a book, you know, the tensile strength of various materials. But this is what you kind of want. I mean, this is what you want to know, you know, because you don't want to break things. So maximum stress equals a tensile strength, just a word. And all it is, well, what's stress? We had stress a little bit ago. It's just F over A. But this is the maximum F over A. Okay? That's all. All right, so the tensile strength is the maximum F over A. And that's what I want to bring. Okay. Now, like I said, you know, look. Material, tooth enamel, compact bone, spongy bone, spider silk, tendon, cartilage, blood vessel. So these are the values of the Young's modulus. And here's the tensile strength, right? The tensile strength. Spongy bone, 5 times 10 to the 6th. Compact bone, 100 times 10 to the 6th. Tendon, 100 times 10 to the 6th. Spider silk, incredible. Look at spider silk. 1,000 times 10 to the 6th. This stuff's really strong. You know? Okay, so all I'm saying is all this stuff we're talking about with restoring forces and tensile strength and all that, it can be applied to biological materials. And so if you're a pre-med student, you should pay attention. All right. Ugh. Okay, so everybody, okay. So bars A and B are attached to the wall on the left, and they're pulled with equal forces to the right. Bar B, so bar B has twice the radius of bar A. And let's see. And bar B is stretched half as much as bar A. Which has the larger value of Young's modulus? Okay, so basically you're going to have to get the formula for Young's modulus and compare the Young's modulus of A with the Young's modulus for B. So just plug and chug. Okay, so everybody pause your video and figure this out. Okay, so we're back. So this was the equation, right? This was, I mean, one of the equations. There's many equations you can use, but this was the equation that had Young's modulus in it. So we want to solve for Young's modulus. So therefore, y equals the force times the original length divided by the cross-sectional area times how much it's stretched. Okay, so we want to figure. Now look at we don't know any of these values, right? And so whenever you have a problem like this where you don't know the values, you know that this is twice that, and this is half of that. Whenever you have something like that, all you want to do is form ratios. So that's kind of an important thing to remember. So let's do it. So YA divided by YB. Well, that's just this mess, right? So FL over A delta L. Oh, man. So be careful. You know, this is the cross-sectional area. This is bar A. Sorry. I should have said like B and C or something, whatever. So FL over A delta L B. Okay. Now, what is that? What do we know? The forces are equal. Great. Goodbye, goodbye. Let's see. The original, does it say that? Okay. The values of L are the same. So goodbye, goodbye. Okay, so let's not get excited. Let's just do that first. So flip, right? Inverse and flip. So you get A delta L B over A delta L A. Okay, now what is the cross-sectional area of B? Well, it's a circle, so it's pi r squared. So it's pi. Now what's the radius? The radius is 2r. So it's pi. Oh, hold on. I'll do that in a minute, so I'm getting ahead of myself. Let's just say it's pi r b squared. So that's A. Then we have delta LB. Here we have pi r a squared delta LA. Okay, now we can get rid of the pi's. Goodbye. Okay, and then if we feel like it, we can do this, which is a good idea. All right, might as well do that too, huh? Okay, now, what is RB over RA? Well, this is twice that, so this divided by that is 2, but we have to square it, so it's 4. And then, what's delta LB over delta LA? So it's this divided by this, which is a half, which is 2. All right, so the answer is 2. Okay, very good. Okay, so anyway, make sure you know how to do that. Yeah. All right, we want to talk about forces and torques and other things. Mechanical advantage. Mechanical advantage. Let's say that you have this screwdriver and you're trying to flip off this lid. Now, before the lid moves, it's in equilibrium, right? So the torques are equal. Okay? So what does that mean? What does that mean? Before the lid moves, the torques are equal because it's in equilibrium. Well, so, here's the pivot, right? Hopefully this is a large force. And what's the lever arm? It's, you do this, you're able to do this because you have a really large screwdriver, right? So basically, okay, let's do this again. So here, they use hammers. I don't know if they use hammers, but they smash these lids into the can, right? So there's a large force here. There's a large force required to pick this thing up. But what's the lever arm? Really, really tiny, right? But here, there's a large lever arm, so you don't need so much force. So this is what I'm trying to say. So the large force of the can with a super, super small lever arm, tiny lever arm. Oops, can't spell. Okay, that has to equal, let's say you're a wimp, so small force U times large lever arm. Okay? So that's called the mechanical advantage. So again, if you want to pop the lid, you take a really long screwdriver, bingo, it's easy. All right, that's all there is to it. Now, here's a true story. Okay, so years ago, we used to own a Camry, a used, nice red Camry. And one day, I went outside and it had a flat. So big deal, you fix the flat. Well, the problem, this is in Illinois, the problem was, so I took the hub, the cover off, and the bolt, it was just rusted. And how they give you these little wrenches in the car? So with this little wrench, I couldn't unloosen the bolt. So then I thought to myself, come on, you're a physicist, think! And then I remembered that we had a pipe, a really long pipe in the garage. So then what I did, so that was the original thing, right? So then what I did, I just took the pipe and I slid it over this wrench, right? So I have this gigantic lever arm now, you know? And then, piece of cake. You know, the bolt just came off, just like that. So ever since, so when we lived in Illinois with this car, I just kept that pipe in the trunk because I didn't want to be stuck somewhere, you know? Okay, now, some of you lift weights, right? Okay, you have to admit, you know, you can press, most of us can press a whole lot more than we can curl, right? Why is that? Why is that? Well, let's see. It's all about torque, you know, and lever arms. Okay, so here's the question. What is the lever arm or moment arm about the elbow? Okay, what is the moment arm about the elbow? So what we're saying is that this is the rotation axis, right? Okay, this is the force. So just do what you always do. Here's the force line. What's the lever arm? Perpendicular distance from the axis of rotation to the force line. Well, what's that? It's almost nothing, you know? So the lever arm is really, really small. And if you have a really, really small lever arm, the torque that you can generate is going to be really small. And that's why most people can't curl very large weights. All right, let's do an example, and then we'll quit. So everybody read that, please. All right. Oh, boy. So a shot putter holds a shot in her hand. Forearm is horizontal. She can support the shot in this position because of the flexor muscle, which is applied perpendicular to the forearm, right? The forearm weighs 22 newtons, has a center of gravity shown. Find the magnitude of M and the magnitude and the direction of the force supplied by the upper arm bone to the forearm at the joint. Whoa! Okay. All right. So this is a good problem to do, you know, because we get to use all this stuff that we've learned to the human body. Okay, so first of all, you know, the torque is zero, right? The shot putter is holding this ball, and so the ball is not moving. And this is the axis of rotation, and so there's no torque. So let's figure it out. So for part A, the sum of the torques. Okay, we know it's equal to 0. All right, let's just figure it out. Okay, so what are the forces acting on? So what's the object? Well, the arm, right? The arm. This is what's going to rotate, right? Okay, so what are the forces acting on the arm? Well, there's this thing, right? So that's the force, M. And what's the lever arm? Oh, they tell us. Isn't that nice? Okay, so here's the force line. Here's the perpendicular distance between the force line and the axis, 5.1 centimeters. Now look, we're going to keep it in centimeters, and you'll see why. You can do stuff like this with torque. You'll see. Okay, now hold it. Sine. This is going to make the arm rotate counterclockwise, so it's a plus. So it's a plus. Okay? Then what do we have? Then we have the weight of the arm that's down. And they said that the weight of the arm, 22 newtons. I'll put it in. I don't know why. I will. So this is going to, right? So there's the weight, and it's going to make it clockwise rotation. So it's minus. So minus 22 newtons. What's the lever arm? They didn't tell us. That's okay. So they give us this distance, 8.9. They give us this distance, 5.1. So that's 14, right? So it's 14 centimeters. Okay, and then we got the shot. Okay, so the weight of the shot, where does it say that? 39.2 newtons. Oh, hold it. If this is the only force acting on it, it's going to rotate clockwise. So I have to give it a minus sign. And what's the lever? Okay, so here's the force line. What's the lever arm? 33 centimeters. Okay, so what we're supposed to do is solve for m. So let's put this thing and this thing on the other side. So we're going to have 22 newtons times 14 centimeters plus 39.2 newtons times 33 centimeters equals m times 5.1 centimeters. So divide by 5.1 centimeters, divide by 5.1 centimeters. And see the beauty of this? You know, there's no reason to convert to meters, none whatsoever, because we have centimeters here, centimeters here, centimeters here, so they go away. Super, super cool. So we do that, and I promise you, you get, oh yeah, this is a force, right? Right? Okay. So, see, notice it says force, uppercase M. Usually we think of M as a mass, but here they said uppercase M is a force. All right. So you solve this, and you get 314 newtons. All right. So there you go. Now let's do B. Okay, B, find the magnitude and the direction of the force applied by the upper arm bone to the forearm at this point. Okay? Wow. Well, let's just do it. And now think about it. I mean, this is a heavy shot put, right? And so this arm wants to rotate like this, agree? So just think about it. If it wants to rotate like this, what has to be the direction of the force here? It has to be down, right? It has to be down. But we'll just do it. We'll figure it out. Okay, so now we got to do a force diagram. But we got to be careful. Well, we don't have to be careful. We'll just do it, okay? All right, so what we're going to do, I'm kind of thinking of this as like the pivot point now. But don't worry about it. Okay, so let's just draw the force diagram. But it's going to be a complicated force diagram, okay? Hope you don't mind. So here we have the shot put, 39.2 newtons. Okay. Here, I hope you agree that this force has to be down. So I'm going to call it F. And if I'm wrong, we'll just get the wrong sign, right? Okay, up, we have M, which was 314. I erased it, sorry. M, and then what else? Right here we have the 22, right, from the arm, right, the weight of the arm. Okay, so those are the only forces, right? And again, if you didn't know this was down, you could have just made it up and you would get a negative sign. Okay, so that's it, right? The M is 314, this is only 22, this is only 39.2, so this has to be down, agree? So basically, so we have F plus 22 newtons plus 39.2 newtons equals 314 newtons, right? The up forces have to equal the down forces to be in equilibrium. So therefore, F equals 314 minus 22 minus 39.2. And I promise you that's 252.8. There you go. Okay? And again, I think the easiest way to think of this is just think of this as the rotation axis. This wants to pull it down, right? So hold on, let me get to my meter stick. So think of this as the rotation axis for part B. Right, the shot put wants to pull it down. So here, this force better be this way for this to be in equilibrium. Okay, all right. Let's review. Okay, so we talked about torque again. We solved problems with torque, balancing forces. We learned about, well, we didn't learn about center of gravity. We learned about that last time, but now, when we do our torque problems, we realize we have to put the weight at the center of gravity. And we talked about stability, the critical angle and all that. We talked about restoring forces, spring forces, understand how spring-like restoring forces act during the stretching and compressing of rigid materials and bones, biological materials. So, okay, equilibrium now. If something can rotate, some of the forces equal 0, some of the torques equal 0. And again, I would always, if I have something, a rotational problem, I always do this first. I might be able to solve the problem. If not, then you have to do this, like the ladder problem. Make sure you understand that. Okay, here's the stability thing. Theta critical, okay, the restoring force, and stress is proportional to strain, and this whole thing about linear. And what we really care about is elastic, right? If it's elastic, it goes back to its original shape. Here it's permanently deformed. Here it breaks, right? If you pull it too much, it's going to break. So tensile strength, you need to know what tensile strength is. The mechanical advantage. Here, with a long screwdriver, you're using a long lever arm, so the force doesn't have to be so great. And you can piece of cake, right? And then make sure you understand this problem. That's it. Thank you.